All right, so this question says, practice the art of recognizing patterns of resonance and using curved arrows to push electrons and show their delocalization. So we'll start with the closed square bracket, which means that we're going to be drawing resonance structures. We're going to put a resonance arrow here, and then we're going to try to identify where or how we could draw a resonance structure. Well, I noticed a couple of things in here. One of the things that I noticed right off the bat is that we have a charge, we have a pair of electrons right next to a carbocation. And so we could dump that pair of electrons, we could put those electrons here to make a bond and give both of these atoms a complete octet. And we could do that. So let's start with that. And I'm not the best at drawing 7-membered rings, but I'll do my best here to draw it as well as I can. So we have another nitrogen here, and then like that. There we go. Like this. You know what I'm going to do is I'm just going to copy and paste this. So let's say copy and paste it down here because I'm going to need another one. Anyhow, let's finish it up. So we've got our CH3 group over here. We've got a pi bond here. We didn't touch anything else, so we'll leave everything else intact. There we go. Like that. Put our negative charge here. And there we go. So there's our first resonance contributor. Can anybody tell me, is there anything missing in this resonance structure the way that I've drawn it? I'll give you a clue, there is. There's something missing. Could anybody tell me what's missing here? It's a positive charge, right? I had a positive charge over here. Yeah, thanks, Allison. Absolutely. Absolutely. Oops, I didn't mean to do that. Yeah, I'm missing the positive charge right here. Okay, I'm missing the positive charge on the nitrogen. All right, so we got that. What else could we draw? We've got an allylic lone pair, don't we? Because we have a pi bond right here, then we have a sigma bond, and we have 3 lone pairs in this oxygen, so we have allylic lone pairs here. So we could draw a resonance contributor for that. We could take this pair, make a pi bond, and we could put this pair of electrons over here like that. And that would give us a new resonance contributor. Let me maybe move this over a little more to make this as neat as possible. So let's draw what that would look like. We still have this bond. We still have that lone pair. This hasn't changed. We still have the positive charge here. But now we have a pair of electrons here. And so we have a negative charge here. And we've got a double bond here. So there you go. So there's another resonance contributor. And there's also another one, isn't there? Because I have another allylic lone pair now. I've got pi bond, single bond, allylic position, and I've got a lone pair on it. So I can draw one more resonance contributor, can't I? So just going to move this over here. And let's draw that final resonance contributor. I'll put a pi bond here, and I'm going to move these electrons over here like that. And what's that going to give me? Well, I didn't change anything down here. I still have my double bond here. Now I've got a pi bond here, my CH3, and there we go. And that's my final resonance contributor. And so we were able to draw a total of 3 resonance contributors from what we started with. All right. Keep in mind that if you're starting out with something that's neutral, right, you've got a positive charge and a negative charge. So overall, the charge is 0. That means the charge of every resonance contributor has to be 0. And you see the charge here is 0, the charge here is 0, and there's no charges here. So everything is neutral there as well. Well, with that in mind, I wanted to take a look at some practice problems from our textbook. I'm going to switch over to a blank document. And I wanted to take a look at some of the questions in question 2.52. So this is 2.52A. So if we're starting out with this guy, like this, okay, it's asking me to draw the resonance contributors. All right, so what do we see in this one? Well, I noticed that we've got an allylic lone pair because we have a pi bond, single bond, and then we have a pair of electrons over here. So let's draw the resonance contributor. We're going to take one of those lone pairs, make a pi bond, and then we're going to take the pi bond and break it and put the pair of electrons on this carbon, allylic lone pair. And let's draw what we end up with. It's going to look like this. So we end up with this. We have a pair of electrons over here. And we have a lone pair right here. So we started out with something that was completely neutral. Here we have a positive charge on the oxygen, and we have a negative charge. Maybe I could draw my carbocation, or my carbanion rather, a little bit better. So we have a negative charge on this carbon. All right, let's move on and take a look at B. So in B, what have we got? We're starting out with a ring, and we have a positive charge. Right here, we have a carbocation. So now we've got a lone pair adjacent to a positive charge. And so we can take this pair of electrons and dump them in here to make a pi bond. Maybe I could make that arrow a little better so that it ends right between the atoms, like this. And then I'm going to end up with this resonance contributor, where I have a pi bond here, a pair of electrons here, and a positive charge on my oxygen. So again, here we use the allylic lone pair, and here we had a lone pair next to positive charge. All right, let's take a look at C. In C, we have this exocyclic double bond right here. We've got a positive charge here, and so we've got an allylic carbocation. So we can dump these electrons into here. And what's that going to give us? Well, let's draw it. We're going to have our double bond here. And then we would have a carbocation out here. So this is an allylic carbocation. Let's try D. In D, we're starting out with nitrogen like this. And so in this one, we have a pi bond between atoms of differing electronegativity, right? Nitrogen has an electronegativity of 3.0. Carbon has an electronegativity of 2.5. And so the electrons are going to be drawn towards the more electronegative element. And so let's draw what we would end up with. Now our nitrogen has two lone pairs. And so it's going to have a negative charge, and our carbon is going to be electron deficient, so it will be a carbocation. So we'll put here pi bond between atoms with differing electronegativity. Let's take a look at E, which deals with an aromatic compound. So this is a good one. These are really common questions on quizzes and exams. So we'll start out by drawing our aromatic ring. And then we have a nitrogen attached to the aromatic ring, and there's a lone pair on it, right? We have an allylic lone pair. We have a lone pair, single bond, pi bond. So let's start by drawing the first resonance contributor. We're going to take that lone pair, we're going to make a pi bond, and we're going to break this one and put the lone pair out here. So we end up with a carbanion, and we end up with a nitrogen with a positive charge. I don't know why that turned into a circle. I didn't mean to do that. There we go. Maybe I'll draw it like this. There, like that. Okay, so we end up with our six-membered ring. We didn't do anything with this pi bond or this pi bond. Now we have a double bond to our nitrogen, which has two hydrogens attached to it, and we have a lone pair here and a negative charge. Well, we've got another allylic lone pair, don't we? We've got a double bond, single bond, and a lone pair. So another allylic lone pair. Let's keep moving those electrons around the ring. So we make a new pi bond. We break this pi bond. We put the electrons here. We make another resonance contributor. So now I've got two pi bonds here, another one here. these two hydrogens. I've got my positive charge on my nitrogen, and I've got a negative charge down here. I can keep going. I've still got another allylic lone pair. So let's move those electrons around and make a new pi bond. Take these electrons and move them up here. And then I end up with this. So I have a new pi bond here. This one, I have a pair of electrons here with a negative charge. I have my nitrogen and a positive charge on it. And then I still have another allylic lone pair. So I have a lone pair, single bond, double bond. So same thing. I'm just repeating the same pattern over and over and over. There we go. And now we're going to start right back from whence we came. So, oops, I'll draw the pi bonds the way that they are here. And there we go. Now we're right back to the starting material. And there you have it. So we've drawn all of the resonance contributors for this molecule. Give me a thumbs up if you follow me on that one, because it's very important that you are able to draw resonance contributors for an aromatic ring. Good. Thanks, Jonathan. Excellent. All right. Let's try F. So this is still the same question. It's question 2.52. 2.52, and now we're on F. We're going to start out with this interesting compound, which has a whole bunch of pi bonds in it. So we've got this exocyclic one here. And we have this guy, and then we have this one here. So this is just a matter of allylic pi bonds, or allylic lone pairs rather, moving them around and around and around. So I'm just going to fix this pi bond a little bit. So look, I'm not a big speed guy. I'm not a big guy in terms of like timing myself on things, but you should be able to draw these resonance contributors, relatively quickly, so that you can say, okay, well, I've had an allylic lone pair there. So now I'm going to draw this guy where I've got a carbanion here. I made a pi bond here. Now I'm going to take this pair. I still have another allylic lone pair. I'm going to push these electrons over here. I'm going to end up making another resonance contributor where I have a pi bond here, another pi bond there. I still have this one. I have the lone pair here. And then I can do it again. Make a new pi bond here, move these electrons over here. Another allylic lone pair, right? That's all I'm doing. Allylic lone pair over and over and over. And then I'm going to end up with the final resonance contributor where I have these two double bonds in the ring. I have a carbanion on the end here, and then I have this double bond over here, and that is my final resonance contributor for F. All right, let's try one more. Let's try 2.52G. This one. So this is 2.52G. So we're starting at this molecule is called acetophenone. You don't have to know that now, but sometimes it's just nice to hear the name of a molecule. So it's this guy. It's a ketone, and it's also aromatic. Okay, so let's see if we can draw some resonance structures here. The first thing I notice is that we have a pi bond between atoms of differing electronegativity. So we're going to start by breaking that pi bond, putting the electrons up on the oxygen, and then what are we going to end up with? We're going to end up with this guy. So our 6-membered ring, just going to do it like this. Like that. And I'm going to copy this and paste it just to make my life a little simpler, because I'm going to need this structure a few times. Here we go. Okay, so what are we going to have after we've done this first resonance contributor? Now we're going to have a negative charge up here. Our pi bonds remain unchanged, but now we've got a carbocation here. So now we've got an allylic carbocation, don't we? Look, we've got pi bond, single bond, and a carbocation. So let's push some electrons. We're going to take these electrons from the pi bond, make a new pi bond, like that. And what's that going to give us? Let's see. We're going to end up with something that looks like this. where we're going to have a double bond here. We're going to have a carbocation here. These pi bonds remain untouched. And we have a negative charge over here. We have another allylic carbocation. So try pushing those electrons. While I copy and paste this stuff. There we go. So same old thing. We're going to push those electrons. Oops, I need a pen to do that. There we go. So we're going to move these electrons over here. Remember, with an allylic carbocation, only one curved arrow is required. So now I've got a pi bond here, a pi bond here. I've got one here. And I got this. And I have my positive charge over here. I have another allylic carbocation. I only need one curved arrow, don't I? So I'm just going to make a new pi bond there. Put this over here. Like this. And then I'm going to end up with this resonance contributor. Where I have the pi bond here, one here, one here. I still have the negative charge on my oxygen. Don't know what happened there. And I have carbocation here. I still have another allylic carbocation right here. So I'll use my red pen, dump these electrons in here, and I'm right back to the first resonance contributor that I drew, where I have all the pi bonds here. I have my negative charge here, and I have my carbocation. Right, so this resonance contributor and this one are identical. So I'm right back to the beginning, and there you go. We drew all the resonance contributors for this molecule. So again, you've got to be able to recognize the patterns for resonance arrows in order to draw resonance structures properly. Well, I want to cover one more section that deals with resonance structures. Just give me a second here to find it. What am I doing here? That's weird. There we go. And it deals with assessing resonance structures, because we've looked at drawing all these different resonance structures, but not all resonance structures are equal, meaning they're not equal in the amount that they contribute to the overall resonance hybrid. So let's take a look here. It says that many molecules have multiple resonance contributors. We just practiced drawing some, where not all the resonance structures contribute equally. And there's some rules that we can use to assess which resonance structures contribute more to the resonance hybrid than others. And they're pretty, I don't like to use the word simple in organic chemistry, but I think they're pretty easy rules to follow. The first one is that the most significant resonance forms have the greatest number of filled octets. And I've referred to this a couple times today already. Right? This is a great resonance structure. There's nothing wrong with it. There's nothing wrong with this one either. However, this one would be a major contributor. Why? Because this carbon does not have a complete octet, whereas here the carbon does have a complete octet, and so does the oxygen as well. So it's just a matter of completing more octets, and that's why the second structure would be a major contributor. Rule number 2, you've seen lots of resonance structures that have formal charges, but you've also seen some resonance contributors this morning that don't have any formal charges, haven't you? Well, the resonance contributors that have no formal charges, or the ones with the fewest formal charges, are going to be the most significant. So we have 3 resonance contributors here. The one that has no formal charges is the largest contributor. Then we have 2 other ones here, right? They both have a positive and a minus charge in them. The reason that this one is going to be the least significant in terms of its contribution to the overall resonance hybrid is because this one, the carbon doesn't have a complete octet, whereas in this one, even though we have charges, all of the atoms have a complete octet. Rule number 3, a structure with a negative charge on the more electronegative atom is going to be more significant. And if we have a positive charge on a more electropositive atom, well, that's going to be a more significant resonance contributor. You look at these two resonance contributors, nothing wrong with either of them. All the atoms have complete octets, except for the hydrogens, of course, which have complete duets. But in the first one, the reason it's the major resonance contributor is because the negative charge is on the oxygen. Right? We know that oxygen is the second most electronegative element. It has an electronegativity of 3.5, whereas carbon is only 2.5. And so since the negative charge is on the carbon here, which is a less electronegative element, it will be the minor contributor. The same thing applies to these two resonance contributors. Here we have the positive charge on an oxygen. Here we have the positive charge on the nitrogen. Well, nitrogen is less electronegative than oxygen, and so it's going to be more content or more stable with that positive charge on it than an oxygen would. Therefore, this will be the major resonance contributor. Rule number 4, if a compound has an overall formal charge, focus only on drawing resonance forms that show the delocalization of that charge. Okay. Another way to put this one, I think, would be to say, we try to avoid having multiple charges that are the same. Right? Here we have a negative charge in our first structure. So that means that any resonance contributor that we draw should only have that one negative charge, right? Similarly, if we had one positive charge, any resonance contributor should only have one positive charge, right? So now here you've got two negatives and a positive. That's going to be insignificant, right? You're developing new charges for nothing.